All right, so let's work on this problem. We've got a frame. It's fixed at A, fixed at B. It's got these distributed loads, both vertical and horizontal. And I want to find the horizontal displacement at C. So here's C. I'm looking for the horizontal force. So we're going to use virtual work for this. So if I'm looking at this, say, section here, someplace between A and B, we need to decide if we work the left side or the right side. Left looks very appealing, but I don't want to go to the trouble of finding all those reactions because I have to resolve all these forces. And I mean, it's not hard, but oddly enough, I'm going to go to the right. And then when we cut somewhere between B and C, now in this case I think the selection is a little clearer. I would definitely work the, in this case, the lower section. There's less to deal with there. So with that as a background, let's begin. So I'll first do section AB, trying to put together the moment expression for that. So let me kind of sketch it in. So I've got a distributed load here on the end. But I can easily replace that with a concentrated equivalent, which I will. And it should be the area under the curve, which is 8 times 200. That's what? 1,600. Maybe I'll go ahead and convert that to kips and just say 1.6 kips. And the distance from the top down would be half the distance, or 4 feet. Is that okay? So now the top piece has also a distributed load. And I'm going to eventually convert that into a concentrated equivalent. Now this is my cut surface. Let me go ahead and mark in that this is my moment that I'm looking for, the moment at AB. And where should I make my coordinate? I think it's going to be a lot easier to go this way. So with that said, what would this equivalent force be? Well, the base would be x and the height would be 400. So it would be 400x, or in my kip notation, it would be 0.4 kip x, right? Well, it's not 0.4, it'd be 0.4x, and that's kips. And from the cut, what's the distance? What's the total distance, x divided by 2? So now I can come in here and sum my moments at the cut. I'm using right-hand rule for my sign convention. Make sure everything's in equilibrium. So starting here at the cut, what kind of moment is that? That's a negative. So I've got negative the moment in AB at that cut. What about this 0.4x force? Positive or negative moment about the cut? Negative. So I've got negative 0.4x is the force, and the moment arm is x over 2. And then I've got this 1.6 kip force. What kind of moment does it create about the cut? Negative. And that has a moment arm of 4. So I should be able to solve for the moment in AB. So what would that be? It looks like that's going to be, I've got 0.4 divided by 2, which is negative 0.2x squared, minus, what's that, 6.4? What's 1.6 times 4? 6.4? And that should have units of kips and feet. So there's my moment expression. Not too bad. Any questions about that? So let's go to the next section, which would be BC. So in that case, I'm looking at just the little bottom piece, and I've got my distributed load pushing to the left. Internally, I have my moment at BC, and I think I'm going to measure that from the bottom up and call that Y. So what's my concentrated equivalent force here? Would be 200 pounds times Y, which that's going to be 0.2 Y, right? I'm doing everything in kips. And the distance from the cut down? Y over 2. Everybody see that? So now when I sum moments about the cut, make sure I'm in equilibrium. Using right-hand rule, that moment is negative. And the applied force is also negative. So the force is 0.2 Y with a moment arm of Y over 2. So the moment in BC is going to be equal to negative 0.1 Y squared. Can I check this? Do these two moment equations have some place in common? Yeah, at B. So in the first one, at B, that would be when x is 0. So I put x equals 0, I get negative 6.4. B for this one is when y is 8. So I got 8 squared is 64 times a tenth. Hey, 6.4. Seems to work. So I feel pretty comfortable that my moment equations are correct. So now what do we do? Well, let's go back and do the virtual system. What's my virtual system look like? Well, the geometry is the same. We've got the same structure. Now let's consult the problem. The problem says I want the horizontal displacement at C. So here's A, B, C. I want the horizontal displacement, so I'm going to assume my structure moves to the left. So there's my horizontal virtual force at C. Now in the first problem, I chose to cut AB and look at the left side. I have to do that again. Also in the first problem, I decided to cut BC and look at the lower portion. I have to do that again. So let me just delineate this a little bit so it kind of marks it off. So let's do this system. So what does AB look like? Well, I'll draw the same free body I had before. I'm going to have the same coordinate system to the cut, x. I'm now going to have my virtual moment at AB. And don't forget, I've got my virtual load. This is still 8 feet. I forgot my 8 feet there, but I think we knew that. So now I'm going to sum moments. So again, right-hand rule is my sign convention for my moments. I'm going to look at the cut, make sure I'm in equilibrium. This internal moment is negative in my sign convention. And the moment created by the virtual force is also negative, so it'll be force minus, 1 times 8 feet. So it looks like my virtual moment in A, B is minus 8 feet. It's not too bad. So now if I go to BC and draw my free body diagram for that, I have my horizontal force. I assumed up was called Y. My moment was this way, so it'll be the same direction, except that's going to be the virtual moment in BC. So again, I'm going to sum moments at the cut. Make sure it's in equilibrium. Right-hand rule is my sign convention. What do I have? Well, this moment is what? Positive or negative? Negative. And the unit load creates also negative moment with a moment arm of Y. So my virtual moment in BC is minus Y. So what do? Put the pieces together. So the displacement at C in the horizontal direction is going to be the integral. Let's do the AB section first. So that's going to go from 0 at B to 10. 0 to 10. What's the real moment in that section? This thing. So negative 0.2x squared minus 6.4. And the virtual moment? And we'll divide that by E and I, and that's integrated in x. And then I'll do the BC part. I chose a y coordinate that starts here at C and goes to B, so that's going to be 0 to 8. The real moment is negative 0.1 y squared. And the virtual moment is minus y. And that'll be divided by EI and integrated in y. That's good enough for me. I think, though, if we had a couple more minutes, this would not be a very difficult thing to evaluate. In fact, I'll probably finish it off on this piece of paper and post it for you to see. But this is a very doable problem. It only took me 13 minutes, and that's with me yapping and talking and changing pen colors and all that other stuff. Any questions about that?